This video will discuss question 26. In figure 4, a two-stage amplifier is given. Assume CL is 2 picofarads. How will you connect the frequency compensation capacitor, CC, and what should be its value so that you maximize the amplifier stability phase margins? And then as the options we get 8 possibilities. Each circuit is given twice and they are given with different compensation capacitor values. So one of them is 1 picofarad and one of them is 100 femtofarads, which is the smaller option. This is figure 4. We get 4 identical circuits with different positions for our compensation capacitor. The caption mainly contains component values which we will not mainly use in this exercise, so we will just omit reading that. In this exercise we want to pick a circuit and a value for CC such that the stability phase margins are maximized. To maximize this phase margin, we should do 2 things. Firstly, we should push the pole frequency for the first stage to an as low value as possible. And secondly, we should ensure that the pole frequency of the second stage is larger than the unity gain bandwidth frequency. So let's look at the first statement. We should get the pole frequency of the first stage to an as low value as possible. Or which circuit should we pick to reach that result? Well, we can do that by looking at how we compute the first pole frequency. It is the inverse of the time constant at the output node of our first stage. And that's the same as 1 over R equivalent at the output of stage 1 times the equivalent capacitance at the output of stage 1. Now between these 4 circuits, this output resistance will remain the same. So we can safely assume that this is a constant value. The equivalent capacitance can be found by taking CC and then applying the Miller effect, because there is a gain between the output of stage 1 and the other node to which CC is connected. So that will be for now written as A. A is the voltage gain between the 2 sides of the compensation capacitor. From this we can conclude that if we want to reach a low frequency for pole 1, we should get a voltage gain that's as large as possible. So we should pick the circuit of these 4 options that gives us the largest voltage gain between those 2 nodes. And if we look closely, that can be safely concluded to be circuit 1. For the reason that we in this case get the voltage gain from not just our source follower, but also from our cascode. The cascode works in such a way that we increase the output resistance and thereby increase the gain of this amplifier. If we would have connected it to, for example, the middle point between MP5 and MP4, or the middle point between MN3 and MN5, the voltage gain would be weakened by the intrinsic gain of the cascode transistor. In circuit 3, the capacitance is directly connected to ground, so we don't sense any mirror effect here. So from that we can conclude that circuit 1 should indeed be the correct circuit to choose here. So from that we can already eliminate 6 possible answers. There are 2 options left, one with 1 picofarad as a value and one with 100 femtofarads as a value. And to find out which of these 2 we should pick, we have to look at the second constraint that we just formulated. The second constraint is that the pole frequency of the second stage should be larger than the unity gain bandwidth frequency. The reason for this is quite clear if we look at a phase plot. Let's remind ourselves of what the phase margin actually means. The phase margin is the phase that we have left between negative 180 degrees and the phase at our unity gain bandwidth frequency. If we have a pole frequency of the second stage that would lie above omega t, then the second drop in phase would be after this. So then we would have something like this. So at the unity gain bandwidth we would sense very little effect from that second pole. But if the pole would lie before the unity gain bandwidth frequency, then the phase would drop even further before we reach that critical point. So to maximize your phase margin, you should actually maximize the margin between omega p2 and omega t. If we now look at the formula sheet, we can find approximate relations for omega p2 and omega t that are as follows. Omega P2 is given as GM2 over C2 and omega T is given as GM1 over Cc. And from this it becomes really clear that the larger Cc is, the smaller this quotient is going to be, and as a result the larger the margin is going to be between these two frequencies. To maximize the stability phase margin, we should then pick the option with the largest value for Cc, and that is in this case F, because here Cc is 1 picofarad.